you. Thank you, Riccardo, for the nice introduction. Okay, so my talk today will deal with online learning and classification of activities from videos. Mainly will be focused on object trajectories. So this is work coming from a PhD student in our group, that is Vaid Bastani. He's coming from Iran. He's working in this kind of research. So probably people from Genoa already more or less know what I'm going to talk about. Anyway, here you have an outline. I mean, there will be some maths, a lot of maths in the end, in the talk. But I will try to not to go in so much details, because we are just before lunch, so I don't want to stress you too much. Anyway, this is the outline of the talk, so I give you some brief introduction and the motivation of what we are explaining here. We will go in talking a little bit about graphical models, probabilistic graphical models, PGM. In particular, talking about maximum likelihood and maximum a posteriori approach. So we will go to talk a little bit about DBN, dynamic Bayesian network. Again, people from Genoa, they know everything about it, or they should. So we'll talk a little bit how to learn, how it could be possible to learn parameters. That is the basic idea that underlies this approach. Then something about mixture models, how this model, this abstraction will go in for solving, how it's useful for solving our problem. And then how it's possible to learn in an incremental way, so continuously learning from data. And finally, some experimental results from video surveillance application. So let's go into the problem. Let me introduce a little bit what we want to do here. So of course the framework is the one of surveillance, so video analytics. You know that we have several video cameras in London especially, but where basically every time you go around in the city, you probably are being captured by several surveillance cameras, even if you don't know. So people started several years ago to work in video analytics. Video analytics is a process of acquiring videos from cameras and trying to get some useful information from the videos. So you can find a lot of different functions. Some of them are already, say, market products, the most simple one. Most of them are still object of research. So you can find a lot of different research groups in the world. Here I mentioned just a few recent or almost recent references. So you can find a function really related with crowd, so detection of crowd, finding abnormal crowd distributions, fall detections. These are just examples. Then classifying activities, that is the topic, the main topic of this presentation. And specifically trajectory analysis. So starting from trajectory of objects, you can infer several conclusions and find some patterns in the object moving in the scene. So here you will see this will be also the video, the data that we will use for our final results in the final section. So it's a very typical video surveillance traffic video. So a camera that is put somewhere quite high in a building, probably looking at a crossroads. We have pedestrian crossing, vehicle doing different trajectories. So these kind of videos are the videos that we are dealing with. In this case, this is mainly focused on traffic, so different class of vehicles doing different kind of trajectories, but you can have also videos more related to pedestrian walking, but in all these kind of videos, trajectories are a very important part. So in our case, the goal of what I'm trying to explain to you is to find a method that is able, after the tracking, so we will have a tracker, but after that we would like to be able to find different behaviors, so find different trajectories of objects. But we don't want to do it in a static, fixed way, so we don't want to have any a priori knowledge of the scene, so nobody is supposed to parameterize, to configure the algorithm telling how many different trajectories, how many different classes of objects are in this scene, but the algorithm should be able to learn from data, automatically learn which are the trajectories, and automatically be able to create a new class of trajectory as soon as it sees a new one. Okay. So the underlying idea is this DBN, dynamic Bayesian network. You will see some of them in the presentation, of course, but they are very useful because they provide a generative model for trajectory data. So we will have, if we are able to train this kind of network, we will be able to have a tool that will generate different data for different trajectories. So we will see how it can be used both for classifying new trajectories and to classify that an object is following a specific trajectory, but also to find new trajectories. So the DBN, this dynamic Bayesian network, it encodes different states of the system inside the different state of the network itself, and we will have a conditional probability density that is telling us how is probable going from one state to the other. So going, for example, from one position. Okay, in our case, the state I will introduce will be the position of the object in the scene, so the position on the center of the object, for example. How is probable that this object is moving in the new position, given its old one? And this is being defined by this function called CPDs, conditional probability densities. Estimating these parameters of state transition of these probability densities in the DBN is the same of learning the trajectory pattern. So with the technique that I will explain, we will be able to learn different conditional probability densities. So we will be able to characterize different trajectory patterns. Right, so we are putting ourselves inside this Bayesian network, and specifically we will follow two different approaches. One is the maximum a posteriori, when we know some prior on the quantities that we want to estimate, or maximum likelihood that is being applied when we don't know, nothing a priori. So in our model, we can suppose to have this DBN that I briefly explained is able to generate new position, and it was also able to, let's say, explain a specific trajectory, so telling us how it's probable that an object is moving to the new position. But we can suppose to have, let's say, higher level discrete variables that is modifying these probabilities depending on the specific trajectory. So if I am following the straight trajectory, then I will have a DBN. So here I will have a network that is explaining my straight trajectory, while if I'm turning at a certain point, so I'm following a different pattern, then I should modify something in my DBN. This is going to be modified by this high-level discrete variable. So this can be also called switching variable, because it's modifying the behavior of the DBN by modifying the parameters of the conditional probability densities that are involved in the DBN. So estimating this switching variable is equivalent to classify. So if I'm able to estimate the value of this switching variable, I'm able to tell which trajectory the object is following at a certain point. Okay, so let's talk about parameters learning in graphical models. Right, so this is a very basic example of a probabilistic graphical model. So you see here two different variables, y and x. So typically, y is the measurement, the observation, and x is the state. So the fact, in signal processing theories, usually you are not able to assess the state of a certain variable, so you don't know the actual position of the object, but you know a measure, an observation of this position. This measure can be polluted by noise, so it's a matter of this Bayesian framework to estimate the real value of the variables. Better than that is estimating the probability density function. So given a certain, so these probabilistic graphical model showing us two variables, one dependent from the other. So the state, the hidden variables also called, so the hidden state is depending from the observation, that is the y. So our goal here is to estimate the probability density function, the conditional probability density function, so this px given y. So given a certain observation, we want to be able to estimate, to give a function that is describing how it's probable that given that observation y, we have this value in the state x. So these probability density function, conditional probability density function, are typically depending on parameters. So that's why we are interested into estimating the parameters. So the parameters is giving us the shape of the function, basically. So we can have this kind of dependency. So this probability density function can be explained with a function f of this x, y, and theta, where theta is the parameter, can be a vector parameter, of course, can be a single number, depends. But we can have also a more, let's say, complex dependency. So this function g is not directly dependent on y, but it is dependent on another function phi that is dependent on y. So we can have this kind of more complex situation. So here in this slide you have some examples. So I told you usually conditional probability function are expressed through parametric distribution. So formula maths that are depending on some parameters. We will see some of them that you should know already. The most used one is the Gaussian. So this is the mathematical formula. You can see it depends on two parameters, so the mean and the variance. And is usually written like this. So this notation means that the value x is drawn from this condition, from this probability density function. So from a Gaussian function with mean mu and variance sigma squared. So we can have a multivariate Gaussian, so a Gaussian in multiple dimensions, and we will have, this will be vectors and metrics, so mean vector and covariance metrics. We will use during the presentation other two distribution. One is the categorical one, so we're saying that X can be, it's a discrete variable, can assume discrete values with probability given by this distribution denoted with a ket of P. So P is a vector with this P1 is the probability of having the value 1, x1. The probability P2 is the probability of having the value x2 for the variable x, and so forth and so on, up to k. So k different classes, k different values for the variable x. The uniform it's a uniform probability of having a value between two values, a and b. Okay, so now what is our problem? So for a single PDF, so we start easy. Say a single probability density function. We are given a set of independent and identically distributed samples. So we measure the sample of a variable. So we pick up the value of this variable for n times. So we get this. We have these vectors with this vector x with the number we picked up from our data, and we want to estimate the parameter theta that describes best the sample set. Okay. So what does it mean best? Best, of course, is relative. Depends. We have several approaches. The first one is the minimum square error. So we want to find the best value of the parameter theta that is more close to a certain value. So giving the minimum square error. So minimizing this value of the error. What we are more interested into is the maximum likelihood. So the parameter theta that better explains the data, or maximum a posteriori, that is the parameter theta that best explain the data, but given some prior. So we have some prior knowledge on the data. Then we have some other approaches, but we will not go into. Okay. So let's talk a little bit about maximum likelihood. So we want to maximize the agreement of the learned model with observed data. So we have this observed data, and we want to find the theta that maximize this agreement on learned model. So we have no prior information about the parameter, so we want to maximize this quantity that is called likelihood, so that's why this approach is called maximum likelihood. So the probability of a certain vector x, this is, as you remember, is the vector that we measure from data, given this theta. So we want to find the maximum of this. I told you that the samples are independent and identically distributed, so we have this relation, so we can transform this p in a productory of all the function f. So let's talk about the problem, a more concrete problem. So just to understand a little bit better what I just said. So let's suppose we have a coin. But we have an unfair coin, a biased coin. So usually in a standard coin, the probability of having head or tails are equal, are 0.5. But we know that this coin is biased, so we want to estimate this parameter theta. So theta is the probability of heads, basically. So if theta is probability of head, probability of tails will be 1 minus theta, that's for sure. So suppose the coin is tossed 80 times, so I pick up my coin and I toss it 80 times.
So the outcome, I write down the outcome. The outcome is 49 heads and 31 tails. So I have this x vector is given by this. So I put all the outcome in a sequence, in a big vector of 80 elements. So we know the coin outcome as a binomial distribution, so another kind of distribution with a parametric distribution, so parameter being theta is the one that we want to estimate. So then the data likelihood, so the likelihood that we have exactly 49 heads and 31 tails can be expressed by this formula here. So we take the products of this binomial distribution. Okay. So we can find the maximum analytically. So you know it. We derive with respect of the parameter theta this function we just found, and we find the maximum. Basically, the maximum is here, 49 over 80. That is quite easy. Okay. Right, so that is the first approach, so the maximum likelihood. So finding the maximum of this measure that is the likelihood, P of x given theta. But let's suppose now we have some prior knowledge of this coin, so we know something already of this coin. So we can apply a different rule that is called maximum a posteriori. And we apply this bias rule that is famous and even overutilized in tracking, that is saying that the posterior parameter probability, that is this p theta given x, is given by the likelihood, that is the one that we already know, so px given theta, multiplied by the prior parameter probability, and then we have to divide by a number that is used for normalizing. So this is the marginal, called the marginalized data likelihood. It's at the denominator of the fraction. So this criterion, this maximum a posteriori criterion, finds the value of theta that maximize this posterior parameter probability. So we want to now that we know we have some prior knowledge, so we want to maximize this p theta given x. So let's go back to our coin tossing problem. So okay, now we have the same coin, but we know that the coin can be taken randomly from a box that is containing only 3 kinds of coins. So we don't have theta that can go whenever we want from 0 to 1, but it can be only one of these 3 values. So we can have in the coin, we are in the basket, we have some fair coins, so some coins with theta equal to 0.5, and some unfair coins with theta 0.7 and 0.45. And we know that is the prior that we know. We have also some probabilities, so basically how many coins of each kind are in the basket. So we know that probability of having a coin with theta equal to 0.45 is 0.555. The probability of having an unbiased fair coin is 0.15, and so on. So we have this prior knowledge. So we can use our bias rule for finding this posterior probability, p theta given x. And this is the formula. Of course, you notice that the sum of these 3 numbers is 1, but because we always pick up some coin from the basket. And so we have to multiply this likelihood, that is the same as before, theta multiplied by 1 minus theta, with the exponential, with the number of times we observe head or tail. We have to multiply it by the prior of this theta, so our prior knowledge. So we will get something like this if we find the graphical this function. These are the deltas of the impulse. We find something like this, and we can conclude that given this prior knowledge, we observe 49 heads and 31 tails. So it's very probable that our coin is coming from the 0.7 subgroup of the coins. Okay, so because this is the highest probability we get. Okay, so always, as we saw, the parameter estimation involved the optimization of some function, so maximization or minimization of something. So like likelihood or a posteriori probabilities, as we just saw. So there are many ways to solve parameter estimation problem. Some of them are, if we are lucky, we have some closed form analytical solution, but most likely we have to follow some gradient descent or ascent algorithm, or some expectation maximization, or we have also a method called Markov chain Monte Carlo that we are going to use in our algorithm. Right, so let's talk a little bit about DBN, the dynamic Bayesian network. So the dynamic Bayesian network can be, you remember the PGM that I showed you earlier, so with X and Y. So dynamic means that it evolves in time. Okay, so we have X is again the hidden state variable. X is a discrete variable, so can assume one of a discrete set of values, while Y is the observed variable and can be discrete or continuous. So involved here in this HMM or DBN, we have two different conditional probability density functions. One is called state transition model, is the blue one, let's say the function that is carrying me to the next state. So the probability of observing the next state, xt, given that in the previous time instant we have xt minus 1. And we have a state emission model that is the probability of observing a certain y given that the state is x. Okay? So this network is evolving in time, so our goal here is to find these two conditional probability density functions. So we have xt is one of these values, so it's a discrete variable. Y can be continuous or discrete. So we can suppose the state transition model, so the function that is carrying me the next state is a conditional categorical distribution. You remember the categorical distribution is the one that is giving us the probabilities of different states. So this can be read that the probability of having a state x, given that the state at t minus 1 is equal to I, is drawn from this categorical distribution. So we have this pi vector that is giving all the probabilities of different states. So pi1 is the probability, given that I'm in the state I, of going into the state 1 in the next time frame, and so forth and so on. We will need also an initial state distribution, px0, so the probability, the initial probability of the whole thing. While the state emission model, so the probability, the density function of measuring a certain observation given a state, can be any distribution with the parameter phi that is depending, of course, on the hidden state. So the parameters to be learned are these encoded in this theta vector. So you see that parameter theta is now not only a number as we had in the previous coin example, but we have a quite long vector of numbers that should be estimated and learned. So there are several techniques out there for, sorry, I'm missing the references, but if you are interested, of course, I can give you some. there are several techniques for learning these parameters of HMM, like Baum-Welch algorithm or this other one, Kaplan-Line expectation maximization algorithm. So, of course, because things are not so complicated enough up to now, so let's complicate a little bit more. So we are interested in learning nonlinear dynamics. So we have nonlinear function, so some kind of function like this that is connecting, let's say, the state at time t minus 1 to the state at time t. Right, so we can write the function like this. So xt is some function, nonlinear function of the previous time instant plus some noise, some omega variable depending on t that can be drawn from a Gaussian distribution with zero mean and variance sigma. So how to estimate the shape of this transition function? So we don't know this shape and we want to estimate from data. That is being applied in our case for trajectory. So we don't know the shape, a priori the shape of the trajectory, and we want to estimate from data. So suppose we want to predict values of an arbitrary function, this fx, x is a vector, and we want to use a set of samples. So these are the samples that we are measuring. So x and y, where x is this vector of values and y is f of x plus noise. So we can use the bias rule. So the idea here is to, okay, the pink dots in the picture are the points that we measure, and we want to estimate the blue line. So also we want to estimate not only in the slot where we have some samples, but we want to estimate also outside, and we would like to estimate also the variance. So how is probable to have points within these two red lines, and how is probable to have it outside. Okay, so how to get this prior, this PF that is our function values prior. So if let this f be a vector of function that is evaluated at n arbitrary points, so we can introduce this Gaussian process. So it's a process that is able to generate Gaussian distributed probability function. This Gaussian process, it can be described by this n0 sigma. So it's basically being described by the covariance function, also called kernel. That is this big matrix here, relating basically two samples of two different functions. So, okay, so this is an example of a covariance function. So this kernel xj and xi and xj can be given by this square exponential function. So you see it's of this form. So if we want to see the shape of this function, it's something like this. And we can estimate the parameters by using some gradient descent technique. Right, so if we want to predict the function value, okay, so now we are in the case that we want to predict where this function is going. We can use this formula, so telling us that given that these functions are being generated by a Gaussian process, each one of the function is itself Gaussian. So the probability of having a certain function f star given d is the data measure, so the position of the objects, is described by this Gaussian function. and the mean function, the mean function and the covariance are given by this formula. So here, if we apply this formula, we can predict the function values, so being the position of the object in the following time frame, but we also know the uncertainty of predicted values. So do you remember that red line in the picture? Okay, so this is called also Bayesian nonlinear regression. So we should know now how to estimate the shape of this nonlinear function given the data. So this Gaussian process allows to estimate values from an arbitrary nonlinear function at some evaluation point given noisy samples of the function. So we measure always samples that are noisy. And it gives both estimation and uncertainty. Right, so let's go a little bit faster. Is it? Right, so we can use the finite mixture models. So in our case, our parameter x is drawn by a distribution. So our trajectory is drawn by a distribution that has this generic form. So as some distribution, each one of the distribution has a pi k probability. So putting into the real world, this will be, f will be related to a specific trajectory. So f of x and theta k. So k is being the class of trajectory, so the car going straight or turning left or right. And we will have k different possible trajectories, k different possible classes. So pi of k is the probability of having this specific trajectory. So of course we learn from data. So if we see like 100 vehicles going straight and just 2 vehicles turning left, so the probability of having the straight trajectory is much more higher than the probability for having turning left trajectories. So in this case, we have both the component parameters, so the parameters of each subcomponent of each function, but we have also the probabilities of each component that is given by this categorical distribution pi. We can, you remember the PGM, the probabilistic graphical model. We can also try to depict this mixture model by using the PGM, and it will show something like this. So we will have the variables xi depending by some other zi parameters and by some theta k parameters. So xi is drawn by this function fx theta zi, and zi is drawn by the categorical distribution of, so giving the probability of each specific trajectory. So often we have some uncertainty about these parameters, so about this pi and theta parameters. So we have one set of theta for each trajectory and different probabilities of each trajectory. So that's why we can introduce some higher level parameters, these alpha and lambda. And yeah, for having conditional, for having this pi probability, we have to have the probability density function of the parameter alpha being expressed by this Dirichlet probability. So an example of this. So here we put some different parameters. So in this case we have k. Okay, this is not directly related to trajectories, but are just a bunch of points in a two-dimensional space. So by using this model, so this mixture model, we can generate several different data. that is good for our purpose because we want to be able to generate data with different features. So in this case, we took k equal to 4, so 4 different classes, let's say 4 different trajectories. That's why you see 4 different colors in the 2 pictures. N equal to 1,000, so we generate 1,000 points from these 2 models. And these are the other parameters that we use. But you can see that by using this mixture model, so with the theta k, that is being a Gaussian in the end, so with the mean mu of k and sigma, the variance, and this parameter lambda, that is the eigenlevel parameter, generating different sets of this Gaussian distributed theta k parameter. We can generate in the end with this model several different types of data, so data with different features. So these are 2 realizations of this model, of the same model, but without any modification of the parameters. So just 2 random realization of the PGM. Right. So back again, we want to estimate this set of parameters pi and theta. So the easiest way, the easiest case, that is not our case, of course, is when we know the number of components. So we know the number of trajectory that we want to estimate, then we can apply some of these techniques. But when we do not know the number of components, we can proceed in these 3 different ways. Okay, the first one is guessing the number of components and use the above methods, but you can understand that it's not the real solution. What we are much more interested into is this Dirichlet process approach. So it's giving us some mathematical grounding for generating new components, so new k. So having this k not fixed at a certain number, but having the possibility to generate much more trajectories as we see the data that are not coherent with the trajectory that we already learned. Okay, just very quickly now. So this Dirichlet process is a distribution of a discrete probability measure. So we have 2 components in this Dirichlet process. One is the base distribution, and the other one, alpha, is called concentration parameter. So basically, through the Dirichlet process, so it's a process that is generating at each new instantiation, each new realization, is generating a discrete probability density function. So something like this. Starting from this distribution, we are able to generate this discrete probability density function. So in this case, we have 6 different possible values. But by varying the parameter theta, we are able to generate much more components. So all these impulses that you see here. So these are 2 realizations, starting with the base distribution, Gaussian distribution. These are 2 realizations of the Dirichlet process with 2 different values of the concentration parameter alpha. So you see that it basically modifies the number of different components being generated. Okay. Right. So we are using this Dirichlet for solving our problem. We are using this approach for generating new trajectory when they are needed. Right. So we can modify our probabilistic graphical model like this, even if this structure is not so good for practical implementation. So this is actually much better. You see here, through the Dirichlet process, we can have an infinite number of potentially an infinite number of different trajectories. And this PGM is based on a process that is called stick breaking process. That is a practical realization of the Dirichlet process. So the idea is to have a stick of length 1 and start subdividing the stick in different subparts according to a beta distribution, beta j. So this is giving us the different values of our pi, so the probability of the different trajectories in the scene. Well, let me jump a little bit. There are some other things that are not so much important for our problem. So let's go into more detail in the algorithm that we proposed for incremental learning of trajectory patterns. So the structure of the system is basically this. So we have a video stream with the position of the object. So y is the position of the object at time t. This q plus 1 is the number of objects. So we have previously we observed an history of objects. So the first object, so y with 1, as a trajectory going from of length t1, capital T1. So that is the first object that we observed in our data. And then we have up to object number q. Now we are in the point that we are observing the next object in the scene. And we are using a particle filtering for tracking the object. So particle filtering in this form that is called RB is Rao-Blackwell-Eyes particle filter is quite used in the research because it is able to give us both the state estimation, so the estimation of the state of the object, but also classify which is the trajectory. So after this filter, we are able to evaluate this probability density function, that is probabilities of the state of object with state x, and the trajectory r. So r is being here used as a variable telling us which is the trajectory, the specific trajectory that the object is following, given, of course, the observation y. So we store all these estimated probability density function inside the memory, and then we are able to apply our algorithm for incremental learning and clustering. Right, so we have a certain object moving, he arrived at the end of his trajectory, so at time tq. So by using these filtering, we are able to estimate the trajectory points. We are able to estimate the flow function, so the function that is actually moving the object, and also knowing the variance of this estimation, so how precise is this estimation. And we are also able to observe, to get from this particle filter also the trajectory class indicator. Right, so let's, yeah, the new object at time q plus 1, we estimate, I mean, the new indicator of the new trajectory is given by this formula here, so basically without going into the details, but it's telling us how it's probable that one object is from a class that I already observed. So this is telling us the probability of the likelihood that the trajectory is from class R, with R minus or equal to K. K is the maximum number of trajectory that I observed, or the probability that the object is actually from a new class. So as soon as I see something that is not described by all the function that I learn from data, then I create a new trajectory. Okay, so I show you some results. Skip this. Okay, so that is our sequence that I show you at the beginning. So we tested it with this video, but of course the plan is to test with a much more larger set of videos and samples. We have cars and pedestrians moving in the scene. The total is 51 objects. We counted 16 different trajectories, so different behaviors of vehicles. Okay, the processing frame rate is 10 frames per second. Right, so K is the number of different trajectory that we learn from this online learning process. So this first graphic shows us how this number of learned trajectories can vary with the parameter alpha. So by modifying this concentration parameter of the Dirichlet process, we are able to generate much more, to clusterize in much more detailed way. Okay, so to generate more different trajectory patterns. So this is showing the growing rate. So at the beginning, we don't know anything about the scene. Okay, so we start tracking vehicles, and we start learning different patterns of movement. So at the beginning, we start with 0 different trajectories and k equal to 0. But moving on with the time, so the red line is the ground truth. So with this alpha equal to 5, you can see the algorithm is pretty much close to the ground truth. The behavior of the algorithm is the dashed line. So it is able actually to identify new trajectories from the data, while it's behaving not so good with a different parameter alpha. So, and the gray zone is the standard deviation of the results. Okay, here we compare the algorithm with some other algorithm with the state of the art. So the proposed one is the yellow line. The other two algorithms actually are not online. So our technique is able to, as I told you, to learn online, to classify trajectory online. So I don't have to wait the end of the trajectory for being able to classify which is the trajectory. So we will have a class indicator that will switch from one trajectory to another when it becomes more probable that the other trajectory is explaining the data. Right. This is okay, a rock curve. So for the abnormality detection. So the idea is to have an abnormal trajectory when I learn a new trajectory. So when I observe, okay, several 100 vehicles moving straight, and I observe one turning left, that will be an abnormal behavior. This one is also quite interesting. So let me explain briefly. So you remember that, okay, this picture, right? I show you in this picture, in this video, is the beginning of the video that I show at the beginning. We'll have the first vehicle turning right and the second vehicle moving straight. So if you see this first graph, so we already learned the first class. So the probability, this is the time from the initial detection of the object. The probability is going up for the class 1. So at the beginning, the two objects are, the object number 2, that is the yellow line here, is starting to be identified as the trajectory 1, because at the beginning, the second object is following exactly the first one. But after a while, so after half a second or maybe less, it is starting to turn right. So the probability of this trajectory being in the class in the old class is decreasing, and then is increasing again because I'm creating a new class k plus 1. Right. So okay. So let me conclude. Well, I try to introduce a little bit the probabilistic graphical model, how this can be useful for modeling statistical problems with the Bayesian approach. So we try to apply this theory, so this probabilistic or graphical model, to a problem in a video surveillance, specifically for trajectory clustering and estimation. And by using these techniques are very nice if you want to use, if you want to learn parameters online. And in particular, if you want to go in much more detail in this theory, you have to look for this Dirichlet process mixture models and Gaussian process that are able to explain in Bayesian framework a number of flow functions, so moving function that moves the object in the scene. Right, and I show you some results in a very typical video surveillance scenario, but as I told you, can be applied also to some other kind of scenes, like a pedestrian in a shopping mall or something like that. Right, so thank you for not falling asleep, maybe. And thanks to Vaid, that is actually the mind behind this work. Thank you very much.